If it's taking longer than 20 seconds to start solving an energy problem, you might be doing it wrong. So in this video, I'll show you a framework that will help you solve 100% of all energy problems in the fastest time possible. Hey, my name is Jason. I'm the founder of nerdnotes.com, and I've personally helped thousands of students ace physics. So in the next few minutes, I want to pass on that knowledge completely for free so you can solve problems not only better, but faster. And so if you want, you can check out nerdnotes.com. Tons of free resources, tons of questions that you can also start practicing today. And with that said, let's actually jump right into the video. This video will be broken down in two parts, basically. The first part will be explaining the framework. And that's going to be, the framework that we're going to be using to solve any energy question. And then, of course, we need to apply it to two hard questions to prove that it actually does work. And so here is the framework, and there's really 3 steps to this, but the main thing that it's centered around is the conservation of energy. Really, the work energy theorem and pretty much all other energy-related theorems and formulas and derived equations come from the conservation of energy. So if you know how to use this well, then you can really derive any equation from scratch, and you can solve any energy problem from scratch as well. And so the first step is to identify the system. A lot of people just gloss over this part, but it's important to identify what's included in the system. For example, if the Earth is included in the system, that means gravity is within the system, and therefore the system can have something called gravitational potential energy, right? If you exclude the Earth from the system, obviously there's going to be no more gravity, and therefore no more gravitational potential energy. So it's important to identify that system, but it's equally as important to identify the initial and the final state of that system. So for example, if it's a ball rolling down a ramp, okay, the initial state would be the ball starting from the top of the ramp, and the final state would be when the ball reaches the bottom of the ramp. Now, once you have those two states, you can move on to the second part, which is identifying which forms of energy exist at each state. So the conservation of energy tells us, hey, the total amount of energy, so if we start off with 100 joules, will be the same at the final state. That's all the conservation of energy tells us. But our job is to pretty much ask the question, what form of energy exist at those two different states? So for example, when the ball or the marble is at the top of the ramp, what form of energy is there? Well, that's going to be gravitational potential energy, right? Assuming that this system is the ball, ramp, and the Earth, all included. Now, as it rolls down and reaches the final state, again, we don't really care what happens in between, at least for the most part. So, of course, if there's friction and stuff, we would have to take that into account. But just looking at the very final state here, what does all that energy turn into? Well, it's going to turn into movement, right? So that's going to be kinetic energy. And so that's just a quick example of what I mean by forms of energies that vary between the initial and the final state. Again, if that was a little bit hard to understand, I'm going to do an example before we even do the questions. That way we're all on the same page, okay? Now, the last step is really simple, just to rearrange and solve for the unknown. Of course, this is physics, and so our main goal is to just derive equations. That's what we're really concerned about. Now, what I've also just included here are just a few quick notes that I wanted to go over, and these are actually very simple and straightforward things. I'm not going to do a deep dive into really any of these things here, but if you do want to sort of learn these things from scratch, maybe your teacher hasn't taught you, feel free to check out the course. I've linked it in the description and in the comments below, so you can go ahead and check that out. I'll also be sure to link some free stuff as well, so that way you can actually review these important concepts. Now, again, I'm not really going to do a deep dive here, but essentially you need to know this equation. So we did cover EI is equal to EF, but really that equation is saying the initial energy plus any work done by non-conservative forces. And so what is that? What is non-conservative forces? Well, non-conservative forces are essentially, or I should say work done by non-conservative forces are essentially a transfer of energy into or out of mechanical energy. And what is mechanical energy? Well, mechanical energy, again, is just a sum of Ke, Pe, and elastic energy. So again, kinetic energy, potential energy, and elastic energy. And so if energy is going from one of these forms of energies into something non-mechanical, so for example, thermal energy, there's going to be a work that's being done, and because again it's leaving mechanical energy, that's going to be negative work that's being done. Now, an example of this would be work done by friction, right? So friction actually is going to take either maybe kinetic energy and transform it into thermal energy. Okay, well, I guess work done by friction will do that, and so therefore it's going to be a negative work done by non-conservative forces. What would be an example of positive? Well, that's if we're giving energy or transferring energy into mechanical energy. So for example, like let's just say you're pushing a box. That pushing force is going to be a work done by a non-conservative force. And because we're pushing it, the box is going to end up gaining kinetic energy because we're giving it a little bit of extra energy that, again, is going to transform into kinetic energy, which is a form of mechanical energy. So that would be an example of positive work done by a non-conservative force. Now again, I'm just giving a quick high-level overview here, so if it doesn't make much sense to you, wait till I solve the example problem in just a second and then see if it makes sense. And if it still doesn't make sense, then definitely check out some of those resources I left in the description, and that will definitely help you out with your conceptual understanding of all these terms. Okay, now let's do a quick derivation example. Again, we're going to do 2 more problems after this that involves numbers, but for right now, I just want to focus on deriving an equation purely with variables, so that way you can see how the conservation of energy works, again, just in terms of variables. Oftentimes it's a good way to see how everything fits together. So that being said, I want to do 2 scenarios, one where the block is sliding down a ramp and we're trying to find that final velocity, but another scenario where it's sliding down a ramp that has friction on it. So if you've already done this derivation before, maybe in class, try to pause the video and do it again for both of those situations that I just described. Now, if you haven't done it, I'm going to go ahead and show you how to do it. So to start, let me sketch a simple diagram here of the ramp and block system. And so we're going to go ahead and call that the block right there. And again, we're going to try to find the final velocity when it reaches the bottom. And so let's go and start deriving now. Again, because energy is conserved in the system, again, there's no external forces to that system, we can use energy at the initial point, or the initial state, is equal to the energy at the final state. And so again, the initial state would be for when the block is at the top, and the final state is for when the block reaches the bottom. So again, now in terms of forms of energy, what form of energy exists at the very top? Well, that's just potential, right? So PE is equal to whatever it transforms into. Now, when it reaches the very bottom, it's going to turn 100% into kinetic energy. Now, keep in mind, this first scenario is a frictionless surface, so there's no energy that's being lost to thermal energy. Okay, so 100% of that potential energy goes into kinetic energy, or I should say 100% of that potential energy transforms into that kinetic energy. So in other words, PE equals KE. It's as simple as that. Potential energy is mgh, kinetic energy is 1/2 mv squared. We can see that the masses cancel out on either side, and then solving this for velocity really quickly, we're going to get V is equal to root 2gh. Okay, so that is the full derivation. It's pretty straightforward, and of course, if you wanted to, you can actually continue deriving this, because sometimes instead of giving you the height that the ramp is at, they give you the distance that the block travels down. So in other words, the length of the ramp. So if you needed to replace h with a equation that contains L in it, what you can do is you can say that this is L, and what we can now do is we can say that this is a right triangle, and assuming that you're given the angle, which in most cases they would if they're not giving you the height, what we can do is we can just use a little bit of trig. So we can say that the sine of theta is equal to the opposite side divided by the hypotenuse, right? So sine of theta is equal to h over L. And then quickly solving this for height, we get height is equal to L sine of theta. So now that we have a formula for height, we can go ahead and now substitute that in for height. And now we have an equation for velocity, but now in terms of L, right? So now we can easily plug in L if we needed to. Okay, now what I want to do is I want to move on to that second scenario that I was talking about. The scenario which is pretty much exactly the same, but this time there is friction on the incline. So I'm going to represent that with maybe like this green squiggly line right here. And so that indicates friction on the incline. So what I want you to do now is I want you to derive yet another equation for velocity, but this time you need to take into account the friction on the surface of the incline. So first of all, we can use conservation of energy again. And so we can say the initial energy transforms into the final amount of energy. Looking at the diagram now, we see that the height is the same as the last scenario. And so therefore the potential energy is going to be identical to the first scenario as well. So it starts off with PE once again. This is again gravitational potential energy. So PE, but this time as the block slides down, it's going to generate some thermal energy because of that frictional forces. And so what we can do is instead of just writing PE, what we can do is we can subtract out all the energy that we're going to be losing. So in other words, some of that energy from mechanical energy, which is again just potential energy, is going to get converted into thermal energy, which we're going to subtract out. And again, it's doing that via the work done by friction. So I guess in plain English, this will read potential energy minus all the energy that we're losing is equal to the remaining amount of energy. And what is that remaining amount of energy at the very bottom? At least what form is it going to turn into? Well, that's going to be movement or kinetic energy, right? So therefore, it's going to be equal to just KE. So again, if you read it to yourself, it should just logically make sense, right? Even if I add work done by friction to the other side, which honestly, sometimes I like solving it that way too. So I can say PE is equal to kinetic energy plus work done by friction. And so the potential energy that you start with transforms into kinetic energy, and the rest of it transforms into thermal energy via work done by friction. So as you can see, when you read it out loud, it just makes sense. And so that's really what the conservation of energy is. It's just a transformation of the forms of energy. And so from here now, we can just plug in all the equations and rearrange and solve for velocity. So just to kind of do that really quickly, we're going to have mgh is equal to 1/2 mv squared plus the work done by friction, which is again going to be the force of friction, times the distance that it slides down. And again, these two things have to be parallel to each other. Now, the good thing is that the force of friction, if I was to maybe make a quick FBD here, that would point along the incline, right? It's going to point up the incline actually. And this thing is sliding down the incline. So that distance that it's traveling is in fact parallel to the force of friction. So what I'm trying to say is that this D right here is really the length of the incline. And this frictional force, we need to replace that with maybe something that we do know. And so my next step is going to be mgh is equal to 1/2 mv squared plus the force of friction, which is usually replaced as mu times the normal force, times distance, which again is the length of the incline that is sliding down. Now from here, if you want to solve from velocity, the derivation will just depend on what you're given and what you weren't given. So for example, if you're given height, then you probably would want to do everything in terms of h. If you were given length, then you probably want to do everything in terms of length. So for example, if we were given length, we'd probably go ahead and use this formula that we derived earlier and just plug this in for height, right? That way we have everything in terms of L. And then we can easily solve for velocity. Same thing with mu and normal force. So in this problem, we probably would be given a value for mu. And then the normal force, this is actually pretty standard. So you can actually find this if you were given the angle of the incline. And so what you can do, actually just to kind of derive it out here, just by drawing a quick FBD, we can go ahead and draw mg pointing downwards, the normal force pointing perpendicular to the surface, the frictional force pointing up the incline. And then we can see that the normal force is actually going to be equal to just the y component of mg, right? So the y component, the vertical component of mg, balances out the normal force. And what component is that in terms of trig? Well, that's going to be mg cosine of theta. Okay, so mg cosine of theta is equal to my normal force, and so therefore you can substitute out n with mg cosine theta. Okay, so there you go, and on this side I'm going to swap out height with L sine of theta. Okay, so there we go, and the last thing that I want to do is just cancel out mass from every single one of these terms, and then you can obviously go ahead and rearrange and solve this for velocity. Now that you hopefully understand how this works, let's go and try to apply it to two harder questions to see if you can get it right. Okay, so here is the first of the two hard questions that we're going to do, and this is actually coming right from my practice set from my course because I've already picked out some of the best ones here. So if you do have access to this, I highly recommend doing all the practice sets within this unit. Now, if you don't have access, it's totally fine. You can go to UBQ, and again, UBQ is just a question bank, and you can sort via the energy unit. You can also sort via difficulty, and you can go ahead and do as many questions as you need, and this is all for free. Once you feel like you are getting good at it, then you can move on to the more advanced questions, and as you can see, there's the advanced label that you can pick from right there. Anyways, going back to this question here, what I want you to do is I want you to pause the video and try to solve this question by yourself using the conservation of energy framework that we discussed earlier. And you don't have to get it right. That's not the point. I just want you to try it out yourself. Okay, now that you tried it out, let's go ahead and do it together. So first, let's read the question and make a quick diagram. So a 2 kg model rocket is launched with a thrust force of 275 newtons. It reaches a height of 90 meters, at which point the thrust cuts out. But the rocket continues moving at 150 meters per second. They want us to find the air resistance force acting on the rocket during its ascent. Okay, so like I said, the first thing I want to do is just draw a quick diagram. This is point A, this is going to be at the launch point, and all my energy is coming from that thrust force, right? So technically that'll be work done by the thrust, and I'm going to be losing a little bit of energy as I climb up to my height of 90 meters basically, right? What am I losing energy to? Well, I'm losing energy due to air resistance. Okay, so there's going to be work done by air resistance. And again, that's going to be negative because it's taking away mechanical energy from the system. And so we're going to include all that in the equation. But just to kind of look at the final point here, this is going to be point B. And again, this is going to be when it reaches 90 meters. Okay, again, does the rocket stop at 90 meters? No, but the thrust cuts out here. So that's why I'm going to use this as point B. Okay, so kind of putting this all into the conservation of energy, we can say that the energy at point A, which is my initial point, equals the energy at point B, which is my final point. So once again, where is all the energy coming from? Well, it's coming from the thrust, right? That's going to be the positive work done by the thrust. So it's going to be WT. And then we have to remember to subtract out all the energy that we're essentially losing. And so the work done by air resistance is going to be negative. And so we can just go ahead and put WA. And the remaining amount of energy, okay, so once I've subtracted out the work done by air resistance, the remaining amount of energy will get converted into the energies at point B. And what forms of energy exist at that point? Well, it has some height, therefore it's going to have potential energy. And we also know that it's moving at that point, right? And so therefore it's going to have kinetic energy. Okay, and so just like that, you've put together a conservation of energy equation. It's that straightforward. And also, I should mention that one of the things that I do like doing a lot is just kind of reading this back out loud in plain English and seeing if it makes logical sense. And so doing that here, we have the work done by the thrust. Again, that's the energy that we're putting in, minus the energy that we're essentially losing due to air resistance, equals, or I should say transforms, okay, so the remaining amount of energy transforms into potential energy, and the rest goes to kinetic energy. And so again, to me, that just makes logical sense, and it should hopefully to you as well, and it should also match up with what the problem is trying to say. So the work done by the thrust is force of thrust times the distance that it goes, and again, that's the height of 90 meters, minus the work done by air resistance, which is really just the force of air resistance times the same exact height that it travels, right? Because it's still acting over the same distance. And so therefore, just times height is equal to PE, so gravitational potential energy is mgh, plus kinetic energy is 1/2 mv squared. Okay, so from here, it's pretty self-explanatory as to what to do. You just need to rearrange and solve this for FA. Now, I know that you can probably just do that yourself, so I'm not actually going to do that, but what I will do is I'll leave the question and the answer to this question somewhere on the screen here, so that way you can check your working. Okay, here is the second question that I originally wanted to do, but I'm no longer going to do it because it's just taking way too long to kind of derive out an equation. It still is a very, very good question, so I do recommend taking a screenshot of this, solving it out, and seeing if you get it right. And I'll also leave a link to this question in the description, so that way you can actually check your answer. Okay, so it's not a very hard problem per se, it just takes really long to kind of derive out. So instead, we're going to do a similar question to this that's going to be a little bit quicker. Okay, so here is that second question, and once again, if you want to pause the video and try to attempt it yourself, feel free to do so. And now let's go and do it together. A spring launches a 4 kg block across a frictionless horizontal table. The block ascends up a 30-degree incline with a coefficient of kinetic friction of 0.25, stopping after 55 meters on the incline. If the spring constant is 800 Newton meters, or newtons per meter, find the initial compression of the spring, disregard friction while in contact with the spring. Okay, so drawing the diagram, we're going to have the horizontal surface that it slides across, which is frictionless, and then we're going to have the inclined part that does have friction. Now, on the inclined part, we were given the angle. We were also given the coefficient of kinetic friction, so we had mu k, and we're also given this distance right here, right? The distance it slides up the ramp before coming to a stop. And so my initial point will be from where I launched the block. And what is responsible for launching it? Well, it's that spring. Okay, so that block is being launched by a spring, and it's a terrible, honestly, little system that I drew there, but I think you get the idea. And they gave us a spring constant, so that's K, but we were asked to find the spring compression. Okay, how much do we compress it by? And what we can do now is we can go ahead and start putting together a conservation of energy equation, but just to be clear, our initial state is going to be from when it's fully compressed, and our final state is going to be up here when it stops moving altogether. By the way, I do want to mention one common thing I see a lot of students do, which is why I picked this question, is split it up into two different motions. Basically, they said this as their point A, so when it's fully compressed, and then when it reaches the end of the horizontal surface, they said that as their final state, their point B. And then what they do is they do a separate conservation of energy equation. So this would be their new point A and then their new point B. And then they try to do it that way. And so they have two different equations. But again, remember, energy is conserved, which basically means that at any given point, the total amount of energy should be the same. So it should be the same here, 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 and here. So it doesn't matter if you split it up into two different pieces and two different conservations of energy equations, or four different, or just keeping it as one. So it's one big equation. That's totally going to work. And so that's what I'm going to do here. I'm going to set this as my point A and this as my point B. So just keep that in mind. So moving the diagram off to the side, let's move that over there. And let's start with our conservation of energy equation. So EI is going to EF basically. Okay, so again, the energy at point A, where's all the energy coming from? Well, that's coming from the compression of the spring, which is what we call elastic energy, so EL. Now at point B, which is my final state, what form of energy exists there? Well, we know that the block stopped moving at that point, right? That's the maximum height it reaches, which means that there's no kinetic energy, and all of the energy is now going to be potential energy. Okay, so at my final state, the form of energy that exists is just potential. So my final energy is going to be potential, and again, this is gravitational potential energy. But again, we can't forget to account for the frictional forces on the inclined surface. Okay, what does that do? Remember, friction kind of removes energy from mechanical energy specifically. So in other words, it's going to be a negative work that's going to be applied on our system. And so therefore, instead of saying just EL, we can say EL minus all the energy that we're losing due to the work done by friction. And again, I probably should be a little bit more careful with my wording here. This is actually the mechanical energy that we're losing, not the total amount of energy. So total amount of energy remains constant, but again, it's going to be negative work done by friction because we're transforming out of mechanical energy. So anyways, just kind of reading this back out loud in English, we have the initial energy, which is elastic, minus all the energy that we're essentially losing, and the rest of that transforms into potential energy. And what I can do from here now is just plug in all the equations. So elastic energy is 1/2 kx squared. The work done by friction is the force of friction times the distance that it travels, and that's going to be equal to mgh. And so again, because we're solving for x, you need to basically go ahead and rearrange this equation to solve for x. But before you do that, you want to ask yourself, are we missing anything? And the answer is yes, we're missing a few things. And so the most obvious thing that we're missing is the force of friction, right? Where we're given the coefficient of friction, which is mu, but not the force of friction. So instead of F, I'm going to write mu times n, which is the equation for F. Okay, so I'm going to replace F with mu times n. So now looking at this equation, again, we still are missing the normal force, so we need to make yet another equation for normal force. And the way we do that is sort of like how we did in that first example problem, where we actually looked at the incline and drew an FBD and sort of made an equation for normal force. So just doing that really quickly so that way you can see, again, this is going to be my FBD. I can really draw it at any point. So this is going to be mg, this is my normal force, this is my frictional force that points down the incline this time because it's trying to move up. And the component of mg, again, that will balance out the normal force, is going to be the vertical component. So again, assuming that this right here is the angle, the vertical component in terms of trigonometry would just be mg cosine of theta. Okay, so that's the cosine component. So the normal force, is writing it out here, the normal force is going to equal mg cosine of theta. So now we can go ahead and plug this equation into n, and then hopefully we're going to get rid of all our unknowns, and then we can just simply solve for x. Okay, so there we go. And actually looking at this, we are missing one more thing, right? And that's going to be the height. And so just like how we did in the example problem in the very beginning, we can make an equation for height in terms of the distance that we're given, right? So that's d1. And so the way I'm going to do that, just kind of doing it in a different color here. So this is going to be my height here. And because this is the opposite side of the triangle, this is going to be the sine component of this triangle, right? So I can say that this height is really equal to d1 sine of theta. Again, if you need to do all the trig out in its entirety, feel free to do so, but this is just a little shortcut that you can use. Okay, so anyways, we can go ahead and now plug in d1 sine of theta for the height. Okay, so there we go. And actually, before I move on, I do want to correct a little mistake that I made here. I had put in n as mg cosine theta, so that's what I put in, but I forgot to bring down that d. Okay, and technically I should have actually labeled it d1 because that's what I'm using in my diagram. So let me go ahead and just put in that d1 there and fix that. Okay, so there we go. Hopefully that looks a whole lot better. And from here, what I'm going to do is all the algebraic stuff. So the physics part is done. The part that I really wanted to teach you was, again, that framework that we applied right here. And so hopefully it makes a whole lot more sense. What you can do now is start applying it to problems from either the question bank or wherever you get your problems from. Just start applying it to the problems and see if you can solve them. Okay, now what I'm going to do is I'm just going to speed run solving this for x, and I'm going to derive it algebraically, plug in some numbers so that way you can check you're working. So to start, what I'm going to do is I'm going to divide mg out from every single one of these terms. So mg is going to get divided out here, and this term as well. So what's going to be remaining will be kx squared, all divided by 2mg is equal to, and then what I'm going to do here is just add this term to both sides. So that's going to be mu cosine of theta d1 plus d1 sine of theta. Now what I'm going to do is I'm going to go ahead and multiply both sides by 2mg and divide by k on both sides. And before I multiply it to this whole term, what I can do is factor out the d1. and then I'm just going to multiply it by my remaining term, which is mu cosine of theta plus sine of theta, and then just take the square root of both sides. Okay, so from here, all you need to do is just plug in all the numbers. And once you plug everything in, you should get a value of around 1.97, and that is of course going to be meters because that is the compression of the spring. And also keep in mind that I did use 9.81 for gravity, and so if you use something like 10, your number might be slightly different than mine, but again, it should be around this range here. Okay, so that pretty much wraps it up for this video. It was a little longer than I would have liked, but hopefully it helped you out in some manner. And so if it did, please leave me a like on the video, and I'll catch you in the next one.